All right, we're continuing our conversation about static and kinetic friction with example 2. A box weighing 5 newtons over here is being pulled by a rope. The coefficient of static friction is 0.8 and the coefficient of kinetic friction is 0.5. And question A, in this scenario, the weight of the box is the same as the normal force between the surfaces. Why are these the same? Well, let's start with a free body diagram of the box. So if we were to draw this here, we've got the force of gravity pulling down. By the way, that's the same as the weight. Gravity and weight are two names for the same thing. We've also got the normal force supporting the box. That's from the floor. We've got this force of tension pulling the box to the right because it's being pulled through a rope. And then resisting that pull is the force of friction. And specifically, if it's sliding, it would be kinetic friction. So if I add some numbers, we know that the box weighs 5 newtons. So I can add that here and say that the force of gravity is 5 newtons. Well, as long as the box is going along a level table or level surface, then it wouldn't be rising or falling. It wouldn't be accelerating in the vertical direction. So it would have to be balanced. So we could confidently say that the normal force is also 5 newtons, right? The vertical forces on the box have to be balanced since it's not moving in the vertical direction, okay? Let's keep going. Question B, how much force does it take to get the box moving? Well, getting the box moving from rest means overcoming static friction, okay? Well, the force of static friction is going to be less than or equal to mu sub s times the normal force. Mu sub s up here was 0.8. So I'm going to pull that number in, and then I'm going to multiply it by the normal force that I already identified in the first question. 5 newtons is our normal force. And so that means static friction will be will go up to and equal to 4 newtons. Okay, so you've got to pull with more than 4 newtons, right? Must pull with more than 4 newtons in order to get the box moving. You've got to overcome static friction. And then question C, how much force does it take to keep the box moving? Well, keeping the box moving is a kinetic friction situation, right? That's sliding. So kinetic friction is equal to mu sub k times the normal force. Mu sub k, we identified that earlier up here as 0.5. So I'm going to use that here. 0.5 times the normal force of 5 newtons gives me a kinetic friction force of 2.5 newtons. So that's how much force is required to keep it moving. And then finally, question D, how does pulling up at an angle make it easier to drag the box along the floor? What does this change? Well, if I pull up at an angle like in this picture over here, where we're changing the angle of the tension force, I could actually show that with a new free body diagram. So let me show you what that would be. So here's our box as before. We've got this tension force now at an angle, okay? I'm going to call that F tense. And this would be some sort of angle theta that we could, if we knew the angle, we could get some more specifics. We're still going to have gravity pulling down. We're still going to have friction resisting. But here's the thing. Since this tension force is pulling up at an angle, it has some vertical component, right? Some of it is pulling upwards. And so as a result, the normal force, which like before maybe was, and pardon me, was maybe like this much, and I'm trying to show that as equal to the length of the force of gravity. Well, the normal force isn't going to be as strong. Instead, it only needs to be maybe like this. And the reason is because the downward force of gravity here is now being balanced by 2 upward forces, all of the normal force and a vertical component of the tension force. So we actually have 2 upward forces and 1 downward force. Therefore, the normal force Well, definitely so. Remember, this was 5 newtons in the previous example. The normal force is definitely going to be less than 5 newtons as a result of the fact that we've added tension up at an angle. Okay? So if the normal force is less than 5 newtons, then what's the other effect? Well, remember, the force of friction is equal to some coefficient, and in this case, we'll say kinetic friction times the normal force, right? Well, if the normal force is now less than it was in the previous situation, less than it was here, right? Then we could confidently say, so if the normal force drops, well then, gosh, the force of friction is going to drop as well, right? So here's my summary statement. By reducing the normal force, we also reduce friction. We also reduce the frictional force. By reducing the normal force, we also reduce the frictional force. And that's what this second part of the question is getting at. All right, so this has been static and kinetic friction.